Large forgings are usually formed directly from large ingots. There are usually serious casting defects such as segregation, shrinkage, inclusions and coarse grains in large ingots, and as the specifications of large forgings continue to increase, casting defects become more and more serious. Therefore, modification and modification are two key tasks for forging large forgings. Large forgings are generally formed by free forging. According to the different forging methods, the free forging process of large forgings is divided into two types, upsetting and drawing. Upsetting is a forging process that reduces the height of the blank and increases the cross-sectional area. In addition to the main application of the upsetting process in the forming of cake forgings, the upsetting process is often used in the forming of many important shaft forgings. The main purpose of upsetting is to increase the cross-sectional area of the blank, increase the forging ratio of drawing length, improve the transverse mechanical properties of the forging and reduce the anisotropy of the mechanical properties. The upsetting methods include common flat anvil upsetting, concave anvil upsetting, tapered plate upsetting and M-shaped plate upsetting. Ordinary flat anvil surface upsetting is the earliest upsetting process used. The traditional theory believes that the center point of the forging is in a state of three-dimensional compressive stress during the upsetting process. And the upsetting is conducive to compacting the core defects and will not produce new crack defects in the core. However, in actual production, it was found that the failure rate of ultrasonic flaw detection for large cake forgings is still high after the common flat anvil upsetting process with large deformation amount. The main reason is that there are transverse crack defects inside. Obviously, the central part of the forging is not always in a state of three-dimensional compressive stress during the upsetting process of the ordinary flat station. For this reason, starting from the concepts of active and passive shaping deformation zones. Two new theories for upsetting cylinders with ordinary flat stations were proposed in the early 1990s, the tensile stress theory of the rigid plastic mechanics model and the hydrostatic stress mechanics model theory of shear stress. Using the method of finite element numerical simulation, quantitative analysis of the evolution law of the stress field at the center of the cylinder in the process of thickening of the ordinary flat station emblem. The results show that the center of the cylinder blank with the original aspect ratio greater than 1.6 is in the process of upsetting. A two-way tensile stress state appears. As the reduction rate increases, the tensile stress at the center point of the cylindrical blank first increases and then decreases. When the critical reduction rate is reached, the tensile stress transforms into a compressive stress, and the critical reduction rate, the drop rate, decreases as the original aspect ratio decreases. For a cylinder with an original height to diameter ratio of 2.33, the critical reduction rate is 35%, and the corresponding instantaneous height to diameter ratio of the forging is 1.129. Therefore, when the billet is opened, the reduction rate should be greater than 40%. But each reduction rate should be within the allowable plastic range of the material. Therefore, the original height to diameter ratio of the cylindrical blank is preferably 2:2. 2. In the upsetting process of an ordinary flat anvil, when the height to diameter ratio of the forging is less than 1, the core of the forging is prone to sandwich defects or honesty effect. The concave anvil surface upsetting method includes upsetting processes such as spherical anvil and dish anvil, which is developed on the basis of common anvil surface upsetting. Compared with the ordinary flat anvil upsetting, the concave anvil upsetting method can increase the hydrostatic pressure inside the cylindrical blank during the upsetting process, and avoid tensile stress to prevent new cracks. Therefore, the ability to forge core defects can be enhanced. However, near the spherical anvil and the dish-shaped anvil, there will be a large range of difficult to deform areas, which makes it difficult for the as-cast structure to be broken in this area. The grains cannot be refined, and the voids are difficult to close. The roughing method of tapered plate was first summarized by Luo Hao in actual production. Later, Liu He and Wang Liandong conducted mechanical analysis on it. The conical plate upsetting method is beneficial to eliminate the deformation dead zone at the end of the cylinder, and because it eliminates the radial tensile stress caused by the end deformation dead zone. It increases the hydrostatic stress near the axis during the upsetting process. But, the upsetting of the tapered plate reduces the deformation of the forging along the axis, so it cannot be used as the main forging method to eliminate core defects. M-shaped plate upsetting is a forging method designed by comprehensively using the three-directional compressive stress generated by the spherical plate and the advantages of the tapered plate to effectively eliminate the difficult deformation zone. M-shaped plate upsetting can greatly reduce the volume of the difficult to deform area, make the deformation of the forging more uniform, increase the degree of internal deformation of the forging, and facilitate the forging of internal pore defects. Drawing is the most important deformation process for large forgings, and many defects need to be eliminated in the drawing process. The traditional drawing process only considers the axial stress in the forging, and ignores the transverse stress. Therefore, the traditional drawing process parameters only include the station width ratio. Anvil width ratio refers to the ratio of the length of the forging deformation zone to the height when the forging is drawn at the flat station, and the reduction rate. It is generally believed that when the upper and lower flat anvils draw long rectangular cross-section large forgings, it is appropriate to have an anvil width ratio of 0.5 to 0.8. When the anvil width ratio is less than 0.5, the axial stress at the core of the forging blank is tensile stress, and the deformation of the core is small, which is easy to produce. Transverse cracks are not easy to eliminate defects. When the anvil width ratio is greater than 1, it is easy to produce surface cracks and corner cracks, and the drawing efficiency is low. The traditional flat anvil drawing methods mainly include WHF forging method, SUF forging method, and TUR forging method. The common characteristics of these methods are large station width ratio and large reduction rate. The advantage of these methods is that they can effectively eliminate the void defects in the core of the blank. The disadvantage of grain refinement is that the forging load is high and a large tonnage hydraulic press is required. The AVO method is a method of drawing an octagonal forging blank with asymmetric upper and lower V-shaped anvils. The advantage is that due to the asymmetry of the upper and lower anvils, a large shear deformation is produced in the core, which increases the deformation of the core and helps eliminate defects to a certain extent. The disadvantage is that the unreasonable process can easily cause the forging axis to bend and the defects move outward, affect the performance of large forgings. This is the forging knowledge of large forgings shared with you in this video. Thank you for watching. Goodbye.